Okay. Once again, if you have a seat next to you, raise your hand. There's still a few people in the back. Yeah, looks like there's a few seats up here, and then I guess that's just about it. So, welcome everybody. My name is Zach. I'm a linear algebra TA here at Georgia Tech. This is my 5th semester TAing this class. I graduated here with my undergraduate in 2022. I'm a double major in math and electrical engineering, and I'm a PhD student in electrical engineering. And I study like space electronics and stuff along that lines. But obviously, we're here today to talk about your midterm. So to go over some basic things. It's on Wednesday. I believe it starts at 6:30. Is that right? It's an hour and 15 until 7:45. We hope to scan all the exams with a grade scope ourselves, so you guys won't be able to see that. And then we'll hopefully have everything graded within a week. So, knock on wood, but usually that's the case. Yeah.
Can we turn on the light like front of the previous?
Say that again?
Can we turn on the light like in front of
I have never been in this room before, so I have no idea where anything is. Is there a set of light switches anywhere anyone can see? Where? Yeah, I think that's usually for AC. Try turning it, but. Oh. Ooh. Oh, no, the other way. Okay, little too dark, Can we get some lights on the back, not the front? Okay, is this good? Okay, I think this is good enough for now. So yeah, I took linear algebra in fall of 2017, and I've been teaching and TAing it ever since. So, and the lights are going down again, and the lights are off. Cool. Is the light switch back there? Is that y'all? Okay. Oh. Sorry, just fiddling with my hands. Okay. We're good? Okay. Cool. No more playing with the lights. So those. Okay. Great. All right. I guess this is what we got. So it's going to be a little dark. Nothing I guess I can do about that at this point. I usually come to these things a little bit more prepared. And I check out the room beforehand, but I have a big deadline at the end of this week, so I haven't had the opportunity to. But so the whole format of this session is basically you guys ask me questions and I will do my best to answer them. It can be anything as broad as what the hell is a span to can you answer question 4.2b from the sample midterm from 2020. We'll get there in a second. So I usually start with like some bigger picture questions. So if anybody has anything along those lines, just raise your hand and I'll point and yeah.
Can you please explain the solution set geometrically and the span of the concept geometrically?
Okay, so the main focus of this exam is that exact question. And the question was, what is span, what is solution set, right? If you can nail those two down and understand everything about that, this exam will be a breeze, okay? And that, I promise I'm telling the truth there. So for this exam, the diagram I usually draw out of how to solve these kinds of problems. But for the exam, you should expect 6 to 7 questions. Usually the same type of format as the practice midterms you've seen, or the samples, or the ones from previous semesters. You have about 4 pages of short response, true or false, 3 or 4 pages of that, 2 or 3 pages of some sort of like open response, find the solution set, tell me the span, draw the both, do whatever. So the way to go about those questions is in any given set of things, I'm going to write this out and then I'm going to go take a step back and explain the difference between span and solution set. So when given a problem, if they ask you to compute span or solution set, there's just this nice diagram I always draw. Where to start, you're always given A and or B. And in this class, when in doubt, if you're given a matrix, the #1 cardinal rule is you row reduce. If you row reduce, you're probably halfway there, okay? So step 1, given A and B, we're going to put it in reduced row echelon form. Okay, this is how we go about finding both span and solution set. So the difference is we're looking for span. Okay, we're looking for the pivot columns of the original A And then I guess I'll turn this vertically. Oh, that's pretty terrible. Okay. We're looking at the pivot columns of the original A, and then we're drawing the linear combinations, create the span of the columns of A. Okay. That one's a little bit less work than what a solution set would be. So for a solution set, if we're looking for that, okay. From reducer or echelon form, we bring it back to equations. And then from here, we move into parametric vector form. And that's a perfectly fine way to leave your set of solutions. And if you know this little diagram, that's how you'll pretty much be able to answer any question on find the span or find the solution set. Okay, so the question was the difference between span and solution set, right?
Yeah.
Right.
Geometric.
Geometrically, okay. So if we start talking about something, we have to talk about a matrix, right? That's the whole point of linear algebra, matrices. So if I give you a matrix that looks like this, okay, they could ask you the span of this, or they could ask you the solution set of this, all right? What the span is we can rewrite any matrix in terms of a vector equation. And the way to rewrite this would be x1 times 2, 4, plus x2 times 1, 2. Okay, and what the span is if we're drawing on a graph, okay, whatever I pick x1 and x2 to be, I'm going to draw where they can reach. So for example, if I pick x1 to be 1 and I pick x2 to be 0, I have 2, 4, this one. Or if I pick x1 to be 2, it goes further, and then if I pick x1 to be negative, we can go this way as far as well, okay? So the span is just any number times that respective vector. What you'll notice here, what is the relationship between 2, 4 and 1, 2? Yeah, they're multiples of each other, right? So what being a multiple of each other means is that kind of tells us things about our pivots, okay? And if we were to follow that chart and put this in reducer or echelon form, we're going to get something that looks like the fact, something that looks like this, okay? You'll notice this here is our pivot, which tells me this is my pivot column of the original matrix. And that actually tells me the exact shape and what the span is. So another really big thing that I write for this, that like when you get your exam, either memorize it or turn the page, write it down just so you make sure you remember this, okay? For the shape of each, like geometrical space, for a span, you define it as, or the shape will always be number of pivots, dimensional in R to the number of rows. Okay. So in this particular case, how many pivots do we have? How many rows do we have? So my span is going to look like a line in R2, a one-dimensional thing in R2. Okay. So span and solution set are kind of converses to each other. Okay. So if span is talking about pivots, what do you think solution set's going to be talking about instead? Free variables. So instead of number of pivots, it's going to be number of free variables. Dimension in, and if the last one's R to the number of rows, this is R to the number of columns. Okay. So what can you tell me about the solution set of this matrix without having to do any more math that you've already done? It's going to be a line in R2, right? We have one free variable, we have one column instead of a pivot, and we have two total columns. Okay. Are there any questions on this? It's a very common question that a lot of people get confused on, and knowing this gets you a very long way from where we are in this class right now. Yeah.
Can you explain the solution set?
Yeah. So this is just like the rule, like this will always be the case of what the geometric shape is of it. And however many free variables we have, I'll actually solve this. So what I'm going to do is I'm going to take 2, 4, 1, 2. To have a solution set, we have to have a B. So I'm going to give it 0, 0. Okay. And from here, if we follow our handy little chart, reduce our echelon form, 1.5, augmented 0, 0, 0, 0, what else? Put this back into equations. It's going to give us x1 equals -1/2 x2. x2 is free, so x2 is equal to x2. And to go from equations to parametric vector form, we're just slapping parentheses on the outside. Okay, so instead write the x vector, which is just x1 and x2 ordered vertically, equals free variable times its vector, how many times it shows up in each equation. Okay. So what we're always going to have for solution set is we're always going to have in parametric vector form something that looks like this. We have the free variables times vectors. Okay, and if we have multiple, they're going to be added like plus x3 times whatever. Okay. We can, without having to go through this whole process, we know how many free variables we're going to have, right? It's just number of free variables, number of not pivot columns. So right off the bat of knowing that, we can say it's going to be as many dimension as we have free variables, because each free variable gives me another thing to change. In R to the number of columns, which is as many entries as I have in my vector here. Is this -1/2 1? That's always going to be the number of columns. That's what that vector is going to have. Does that make sense? Okay. Any other questions on this so far? Yeah.
In this case,
They're equal, right?
yeah, they're equal.
Yeah.
It is equal also like at least R3.
What do you mean? In R3, like a three-dimensional matrix at least? Okay, yeah, totally. So another example where we could do this is if I have 1, 2, 4 augmented with 0, have 1, 2, 4 again, 0, I'm going to have 4, 4, 8. Okay. So what this is going to row reduce down to? It's going to be 1, 0, 0, 0, 1, 2, 0, 0, 0, augmented with 0, 0, 0. Okay. So step 1, reduce row echelon form, always. How many pivots do I have? 2. How many free variables do I have? So my span is going to be a plane, right? And I just realized that this is once again a 3 by 3, so I'm actually just going to erase this bottom row. I can't do that. I'm just going to write a different matrix. I apologize. We're going to do 1, 2, 4, 1, 2, 8, augmented with 0, 0. Okay, so we have a different number of rows and columns. Okay, we'll reduce this. We're going to get 1, 1, 0, 1, 0. Oh, apologies. I'm so used to working with square matrices that I always just add the bottom row. So we're here. How many pivots do we have again? 2. So my span is a plane in. So we just call that all of our 2. Okay. So I need, yeah.
So the 1, 3 rows.
Yep.
Is that a span? Is that a plane in R?
So the span of this matrix here would be a plane in R3, yes. Okay. So looking back over here, how many free variables do I have?
1.
So my solution set is going to be A in, yeah, exactly, right? And if we want to solve that out, we're going to get x1 equals -x2, x2 equals x2. This is for this over here. x3 equals 0. So the x vector is equal to x2, -1, 1, 0. Okay. Any questions on any of this so far?
Yeah.
Yeah.
Why is the matrix on the, from what you can see it's here now, matrix on the left and matrix on the right are both planes? Why one are I know the number of rows, but like if each column was a vector,
Yeah.
would they not be just
Yeah. So that's a great question. So he's asking, why is span have to do with rows? So if we wrote this in terms of like a vector equation, right? How many entries would each of my columns have? 3, right? And we call something with 3 entries in 3 space. Call that a 3-dimensional vector. Likewise over here, we're only going to have 2 entries, so that puts us in 2-dimensional, just x and y. For this one, we have an x, y, z. I know that's backwards for variables, but just think about it in terms of vectors instead of your x, y, z columns. Okay, does that make sense?
Yeah.
Cool.
So the solution set in a 3-row matrix is a line of
For this,
Yeah.
yes, this is a line in R3 is the solution set. Assuming it's consistent. Because can you have solutions if it's inconsistent? No. Yeah,
Can you explain like the difference between the span and solution set?
yes. So it all boils down to the context is essentially what it is. So the question was the difference between span and solution set. I've talked about how to find them and how the shape differs. So what a span is fundamentally is a span is the space where the things that we touch are consistent, okay? So if I have a matrix A, okay, and I draw the span in R2 is this line, pretend that touches the origin. And if I have A augmented with B, and I know B is in the span of A, or the column is A, but I'm just going to write A. If I know that, I know it is consistent. B has to be on this line. Span is what is consistent. If it is in the span, the system is consistent and has a solution. How many solutions? We don't know. We have to turn a solution set. So think of span as where we can get with our columns. Okay. Yeah, if B is in the span, we have solutions, we're consistent. And then from there, we can kind of move on to talk about solutions. So talking about solutions instead, the way I usually like to describe this is I like to think about it as like how I can walk and how I can move, okay? So the span of me walking is this entire stage, okay? That's where I can go, period. I cannot go off the stage. I can't float in the air. That would be inconsistent, and that point is out of the span, okay? But if I want to walk over here, I can just take a step. Okay, that's one solution. Or I can take a step over here and then 2 steps this way. Or I can go all the way over here, I can run around and I can come back and I can stand in the same place. Those are all different solutions, and all of those solutions are in my solution set. So anything in your solution set has to pertain to an end goal. You have to have a B. Okay. That's why solutions, you have to know if you have one before you can solve for what they are. If it is consistent, then you can solve for the solutions. Does that make sense? No, okay. So one of the things about linear algebra that is both great and it sucks is there's like 15 ways to explain any of these problems. And sometimes 14 of them won't click, the other one will. And that's for any student. That's just the nature of linear algebra. You can think in space, you can think in algebra, you can think in all kinds of different terms. But so if I draw my A, okay, I say my A is 1, 1, 2, 2. Okay. The span of this line, or the span of the columns of this matrix, is going to be this, right? This line that touches the origin, but I can't draw, that passes through these points and extends to infinity. Okay. So someone give me a vector on this line, anywhere. Somebody loudly and confidently. 3, 3. So if we're solving for B equals 3, 3. When I say B, I'm talking about AX equals B. Okay. It's 3, 3 on this line. It sure is. It's right there. Okay. Being in the span means this is consistent. Okay. So this is going to row reduce. We're going to get 1, 2, 3, 0, 0, 0. Okay. So it is consistent. It is in the span. But that's, if it's in the span, how do we get there? Okay. So think about solution set, it might make a little more sense to go back out to vector forms. X1 times 1, 1 plus X2 times 2, 2 equals 3, 3. Okay. Someone give me a really easy example of an X1 and an X2 I can pick to get to 3, 3. 3, 0, right? 3 times 1, 3 times 1, 0 times this gives me 3, 3. Someone give me a different one where X1 is 0. Yeah, 0 and 1/2. 1 and 1/2, right? 1 and 1/2. 1.5. 1.5 times 2 is 3. 1.5 times 2 is 3. That gets us there. That's a different solution. But if we draw all of these things, we take it from here and we get it back in parametric vector form. X1 equals negative 2x2 plus 3, x2 equals x2. X vector equals negative 2, 1, x2 plus 3, 0. Okay. So it's just however we pick x2 determines x1. Let me move this to the middle and make it a little clearer. Talk about it. So this is parametric vector form, and this describes your solutions. Okay. So somebody give me a value for x2, just x2. An easy number. 0 is plenty easy. 0 times this is 0, right? So my solution is 3, 0. Is that a solution to this? Right? So I plug in 0 for x2, I get this vector just goes away. And I'm left with my x vector, x1 and x2. x1 is equal to x2 is equal to 0. Okay. Somebody give me a different number for x2. That's also easy, but not 0. 1. Okay. 1 times x2 gives me negative 2 times 1 plus 3. We add by rows like that. This gives me 1. And then did I do this wrong? No, I didn't do this wrong. Did I do this wrong? 1, 1. Okay, yeah, I'm sorry. I'm losing my mind. So we plug in 1 for x2. We get x1, which is this top row, to be equal to negative 2 times 1 plus 3. Negative 2 plus 3 is 1. If I plug in 1 for x1 and 1 for x2, do I get 3, 3? Yes, this is just an example of the different values you can get from that solution set. Does that make sense?
Kind of.
Kind of. I'll take kind of right now. Yeah.
So, during that thing, we would, now if we would say the span solution set, we would just take the vector minus 2, 1, right? But
No.
yeah, that's my question.
So,
What do we do?
how many of you have taken calculus before? Okay, yeah, we're at Georgia Tech. I should have expected that. So when you do like an integral or anything like that, now that plus c sticks out, right? For like a general sort of solution. Okay. This vector with no numbers attached to it is the linear algebra equivalent of plus c. Okay. When we are solving the equation a augmented with b, and b is non-zero, we're going to get this, some numbered vector at the end of our solution set. We call it VP. A particular vector, a particular solution. For those of you that have to take differential equations, it's going to be a pain in your ass when you have to find it. But you're going to have to because you're engineers. Most of you. Yeah, I know. So what this is how we shift our solution set for what we call the homogeneous system. Okay. Homogeneous just means instead of a augmented b, b is just 0, so it's a augmented 0. Okay, 0 vector. Okay. So what this solution set looks like and how we would plot this one. The first place we start is we start with this. Okay, this is just, it is a vector, but we kind of just think of it as a point. Okay, we go to 3, 0, and I draw a dot. Okay, and from here, I move negative 2, positive 1, draw a little dot, and then I move the opposite direction, so positive 2, negative 1. And I draw my span through these lines, or through these points. And this creates my solution set to AX equals 3, 3. Okay, this is my solution for that particular case. Any questions on this so far? I'm going to keep going this for a second, but if you have questions, yeah.
Those are all solutions.
So every point on this graph is going to be a solution to AX equals 3, 3. Okay, yeah.
That graph is span.
This is what we would just call the solution set. This is us plotting the solution set. We can't call it the span of the solution set because span implies we start at 0. You might see that it's just kind of like a tiny little phrasing thing that some people mess up sometimes. It's pretty much fine, but yeah. What we call it when we're solving for AX equals something that's not 0 is we call it a translated span, where in space we're moving something and that's called the translation. Okay, I saw a question here. Yeah.
How do you notate this?
What do you mean notate? Like if they asked you, how do you leave it? Exactly like this. It'll be very clear. It'll say like give values for x1, x2, x3, which you say x1 equals x2 equals x3 equals, or it'll say in parametric vector form. Okay. Yeah.
Well, what did you plot against to get that correct?
Get this graph here. I started with my VP. This is essentially my new origin. Okay. So that's here. 3, 0. Okay. And then from here, I'm drawing all the linear combinations of this or the span of this starting here, which again doesn't make sense because span starts at the origin, but I'm just saying that for clarity.
How did-
So I went -2, 1, okay, and then the opposite direction because it goes both ways, +2, -1. Yeah.
Why is it a module?
Say that again a little louder.
It's not.
It's non-homogeneous.
Is it?
Yes. So that's a great question. If something is homogeneous, if you are solving AX equals 0, where should this line start? The origin. If this is homogeneous, it will touch the origin. If B is non-zero in any capacity, it will not touch the origin. So in this case, VP is 3, 0. B was our 3, 3 that we started the question with. Yeah.
You have access to problems.
Yeah. Let me finish this thing. I'll come back to you. Any other questions on this? Yeah. Parentheses are traditionally used for vectors, brackets for matrices. Yeah. Yeah. Like here?
No, like, that's.
The other way or is this way? Oh, I'm so sorry. Okay, here. Okay. Cool. I'll also send these notes in an announcement as well, and I'll post the review. Yeah.
So when like the question asks for like what is the producer solution, and that's just the vector that does not have a variable attached.
If it asks for the particular solution, it is just that vector with no x2 or x3 attached to it. Just the numbers floating. Okay. Any other questions? Yeah.
So, better meaning non-homogeneous, always going to. Or like say R2, R2, will that ever be non-homogeneous?
So you're saying if the solution set is an R3 and R3, it is all of R3. So how many free variables do we have? Solution set. Well, you said it, right? An R3 and R3. So how many free variables?
Solution span, you have
3 free variables. And how many columns do we have? Okay, so we have 3 columns of 3 free variables. What is that matrix called? It's a 0 matrix, exactly. When can you ever augment that with something that's not 0 and have a solution? You can't, exactly. So yes, it'll always be homogeneous. Yeah. Yeah, so after this exam, we're going to move into something called column space and null space. We only talked about span in terms of the columns. It's just another word for it that I don't know why we don't use yet, but whatever. Yeah. Yes. You get a different question first. I'm just taking questions on this. On the back. Okay. Anything else on? Yeah, right there.
Back to flat. Slide.
Yeah, to the bottom. Like here.
So the first thing is one.
This. That was our span of the matrix A.
So if the second thing through is the shift, how is it a different line?
So that's because we're talking about span and solution set. That's the difference there. They're totally different lines. They don't have anything to do with the slopes of each other. Does that make sense?
Yeah.
Cool. Yeah.
What shows the span?
The span of the matrix A is just your pivot columns, and we just extend those out to infinity. So like for this one, 1, 1, 2, 2, we only had 1 pivot column. It was the first one. So we got 1, 1, we got -1, -1, and we shoot those lines off to infinity, and that's our span. Yeah.
With an augmented matrix, like span and just like mathematics.
Exactly. Because to have solutions, you have to be talking about someplace you want to go. Yeah. Say that again. Yes, you're not gonna have to do it. Okay. Yeah,
Now concerning that, but like generally, we're talking about pivots. Are we also considering, the solution to RD as a pivot?
say that one more time.
So, for example, like, let's look at an augmented matrix like the one red, right? 1, 2, 3, 0, 0.
Sure, yeah.
Yeah, right there, right. Would we consider the zero in the rightmost pivot, if in the rightmost column, if that was a non-zero number, would we consider it a pivot?
Yeah, that, and if we have a pivot on the right side of the augment bar, we call that system inconsistent. No solutions, you can't even talk about solution set. Okay, so that point B would not be in our span. Any other questions on this? Yeah. Okay, if there are no free variables, right? Our solution set is number of free variables dimension in R to the number of columns. So we have a dimension of 0. What do we call something with a dimension of 0? Point. So that'd be like one single solution, right? So you only have 3 cases of numbers of solutions: 0, infinite, and 1. Okay, the only time you can have one solution, so you're consistent and have no free variables with a 0-dimensional solution set. If there are no pivots, then you have a 0 matrix, which means your solution set fills everything because you can pick x1, x2, x3, x4 to be whatever you want. Okay. All right. I think we're going to move on to other questions now. Yeah, what was the question?
Okay, so it was 2.3, problem 7.
2.3, problem 7. Give me just 1 second to get there. Said 2.4, problem 7? Okay. Sorry, my Canvas logged me out for some reason, so I have to just relog in real quick. I don't want to feel liable for that, to be honest. No, you're good. 2.4? 2.4. Alrighty, 2.3, problem 7. This is a question that you should expect to see on your exam. They love these questions with H. So what I'm getting on my side, y'all have already had this due, right? Yeah, this due. Yeah.
Solve.
Okay.
Like you put it in a matrix, and then you just like it's a 3 by 3 matrix.
Uh-huh.
To have zeros on the bottom,
Uh-huh.
and you're trying to manipulate H, so that H equals the zeros. And then H by it equals the zeros. What I don't get is like, what exactly does it mean when it says we'll span R3 unless it's H equals this? It has 3 rows. It'll always span R3, right?
Does it?
Or no, I think that's it.
What is the shape of our span? It's number of pivots in number of rows, right? So it'll be in R3, but will it be all of R3 is the question. So what this question is asking is it gives you three vectors and it says the set of these will span all of R3 unless H equals. So when do we span all of R3? How many pivots do I have to have? Three. Okay. So I have two vectors. Spoiler alert, they're both going to be pivots. Okay. The way I always like to do these, okay. Listen to my words very carefully. When you put things into a matrix, if you are in a matrix, you cannot switch columns ever. Okay. If you have vectors, you can reorganize things. Okay. So what I'm going to do is I'm going to put 4, -3, -1, 1, 8, 1, H, -13, -3. Okay. Now we're in a matrix. Now I can't switch columns. Okay. So I'm not going to waste your time with showing y'all how I row reduce. But you're going to get something that looks like this. Number. That's not. So the important thing here is how many pivots do you immediately see? Two, 1 and 1. Okay. Do we want three pivots or do we not want three pivots? We do not want three pivots. We want this to not span all of our three. So what is it? What does this value have to be? 0. Cool. So that gives me H equals 8. Okay, that would be the answer to that. But what?
So,
Okay.
Say like, it's like a 3D object, like all of our three.
Spanning R3 means between these three vectors at the top. If you can combine these three vectors, if H is not 8, to be any other three-dimensional vector. Does that make sense? And that's if H is not 8. If H is 8, then we can only get with as many as we can with these two vectors. Does that make sense?
Yeah.
So the question like that, you want to move the variable and swap this to the right?
Yeah, so the reason I like to move the variable all the way to the right is so that when I row reduce, it's in this bottom right position, which just makes my life really easy. Okay. Yeah. Okay, well, yeah. Okay. Yeah. So the question was, what if H is not 8? So that's another question you should be able to answer pretty easily for the exam. If H is not 8, what is this number? Not 0. We don't know what it is, but it's not 0. If it's not 0, it's a pivot. And then we have three pivots. We span all of our three. Question back there. If it's in a matrix, no. Okay, and the reason I say that is because do I have like x1, x2, x3 as my columns here? No. I actually have x1, x3, x2. That's why I'm saying be very careful, and if you don't totally understand that, just put them in the columns and treat it the same as like before this. This column second, this column third. Okay. Random matrix, don't mix them. If you're in vectors and you're looking for like a value of H, it's okay. All right. Yeah. How to row reduce an unknown variable? So the reason I do this is because I don't have to. So when I do this process, the next thing I want to do is I want to get this down to my bottom row. So my first step, switching rows 1 and 3. Nope. Or 1 H. Okay. Now what I have to do is I have to try and get rid of the 4 and I have to try and get rid of the 1. So the way I would do that is row 3 equals row 3 plus 4 row 1. That's going to be 0. Let me just write this out. From here, what we're going to get, I'm going to leave this first two rows exactly the same. We're going to get 0, we're going to get 5, and we're going to get H minus 12. Okay. And from here, you do the exact same process to get rid of the 5. Okay, and then from there, you'll get it to be H minus 8. Does that make sense? Okay, cool. Yeah. 2.3, problem 8. Yes, thank God I already have that homework pulled up. Okay, so this question is an example of give a matrix, which is a very fair thing to ask. Sorry, I thought someone's interrupting me. Okay, so knowing how to do something like this is a very common thing. Another common thing would be, well, I'll establish in a second if it comes up. But what we have is it's given us a 3x4 matrix. And it's asking us to fill in these qualifications. Okay, so I like to take these questions one step at a time, and I like to list the things I need. Okay, so the first thing says AX equals B has a solution for infinitely many B. So what does it mean to have a solution for infinitely many B? What does that mean? No. In the case of this matrix, but we're not to that point yet. This first statement doesn't have to pertain to any sized matrix. Just what does the statement mean? If we can get two places, what does that mean we have? A span that is non-zero, right? Does that make sense? If we have a B with infinitely many, yes, infinitely many means free variable. I was getting ahead of myself. You were right. But the first thing it says is we have a pivot, okay? So the first statement says we have a pivot and we have a free variable. I apologize. That's so that's the first thing. So how many pivots can we have at most? Three. How many free variables can we have at most?
1, 2, 3, 4.
Okay, for every number. 2. Okay. So to have a solution for some B, we have a pivot. Okay. To have infinitely many solutions, we have a free variable. We need to have at least one. We can have 1, 2, or 3. We can't have 4 because if we have 4, we're missing that qualification where we have to have a pivot. Okay. So we have to have 1 to 3 pivots and 1 to 3 free variables. Okay, not 0 of either of them. Number 2, B does not have a solution for some B in R3. What does that mean? Yeah.
It's gonna be like a row of zeros.
Nope.
Goes 1.
It can. That's what it gets to when we row reduce. What does that mean before we even get to that point? Like, means does not have a solution. Yeah. What does it mean in terms of span?
It'll go outside of.
It will be outside of the span. So if I need something outside of the span, how many pivots can I have at most? 2. I can't have all 3 to fill R3. You're right. That is the definition of something that's inconsistent. But this is we need at most 2 pivots. Span is being recorded. I know. Oh my God. Okay. At most 2 pivots. Okay. So you sum these two things together. What is the overlap? How many pivots can I have? Or 1. How many free variables can I have? 2 or 3. If I have to have 1 or 2 pivots, I have 4 columns, so that means I can have 3 free variables or 2 free variables. Okay. How many pivots do we want? 1 or 2? 2 is fine. So we're going to draw this matrix down here. 3 by 4. Whenever I'm given a matrix size, I always draw the shape before I do anything else. So the easiest case I can think of without having to hurt my brain with two pivots is just making the first columns look like this. Okay, so I need to have a free variable as well. What does that mean my bottom row needs to be? Zeros in an easy case. It doesn't mean it always has to be zeros. What does it mean for these four numbers? Are they limited to something? Can they be whatever they want to be? Do they affect my number of pivots at all? They don't affect my number of pivots. That's the only thing we care about. Okay, so they can be whatever they want. Okay, I usually just leave a star. In easy case, just think of them as all zero. That's fine. Okay, and this matrix would be a solution to that problem. Yeah.
So, the reason why it has infinitely many is because it has three pivots.
Yeah, so for something to have infinitely many solutions, how many points are on a line? A lot. Infinite even. How many on a plane? No, still infinite.
Oh,
If you want to get into the context of infinities, email me. We can have that talk. You don't want to have it. In a three space, how many points do we have? Also infinite. I'm not trying to trip y'all up. So if we have a free variable, we have infinitely many solutions. Okay, and that just means we have a line, a plane, a three space, some kind of free variable. That's all it means. Yeah, question.
Like this.
Definitions you need to know. Okay.
Like, all right.
So the big ones are just the ones I've already said of span and solution set. Okay, like the shape of it. That's that. Reducer echelon form and row echelon form are pretty straightforward. I don't think we need to define those.
Well, it's green line thing, see what they want to be like. We need to memorize that.
Like the vector equation.
Yeah, like if we just conceptualize it, then no, just put like memorize it.
Well, I mean, you don't have to memorize much because it's just C1 V1 plus C2 V2 plus dot equals B. Okay, that's all you need to know for that. Does that make sense? And the only other definition I would think would be like a particular solution. Which that just means you're solving for a B that is not zero. Okay, it means your solution set is translated, which means it doesn't contain the origin. Yeah.
Practice problem that involves solution set and parametric.
Sure. Do you have a question about this? Okay, let me take this one first. So you said a solution set, just solving for a solution set? Okay. Something that I've seen before is you shouldn't be afraid of large matrices. They suck for you, they suck for us to grade, but you should be able to do them. So an example of that, 1, 2, 3, 4. It's easy for myself. 6. Okay, something like this is the headache to row reduce. If you know how to row reduce, you can row reduce it, right? So what is the first step to get a solution set always? We row reduce. Okay, if we row reduce this matrix, what we're gonna do is we're gonna get 1, 2, 3. 0. Okay. We're gonna reduce the matrix, we're gonna get something like this. Okay. So what this boils down to meaning is from here, we can write these back out in our equations, okay? We can write this as x1 plus 2x3 plus 3x. Oh, I skipped a number. Why did I skip a number? Plus 2x2 plus 3x3 equals 1. And then we get x4 equals -1. Okay, how many pivots do I have? So my span is a what? In R3, plain in R3. How many free variables do I have? 2. So my solution set is A in, good. Yes, 4 columns. Solution set talks about x1, x2, x3, x4, right? So we're in R to that number of columns, number of variables, right? 1, 2, 3, 4. Okay. Does that make sense? All right. So from here, we solve, we get x1 equals negative 2x2 minus 3x3 plus 1. We get x2 equals x2. We get x3 equals x3. We get x4 equals negative 1. Okay. So from here, we go to parametric vector form, okay, and we slap parentheses around everything. This is how I like to write my parametric vector form. Because I have my x2s in a column, I have my x3s in a column, I have my numbers in a column. I have each free variable lined up, makes it easy, so I can put parentheses around. Yeah. See here? Oh, I'm as down as I can get. Good. I'll send out the PDF as well, so you can get it later as well. But we can rewrite this as the x vector is equal to x2 times negative 2, 1, 0, 0 plus x3 times negative 3, 0, 1, 0 plus 1, 0 minus 1, 0. Okay. This is my solution set. How many things can I change at will? How many things can I decide they can be whatever they want? 2 things. That is why we have a plane. Okay. We can change x2 however we want. We can change x3. That's one degree of freedom and 2. That creates the plane. Okay. Secondly, we have that nice shift at the end. What does that mean my B is? It's a 0 or not 0? Not 0, right? Some other little thing I'll say. For any B, it will have a unique particular solution. Okay. You don't have to think about that too hard. But I promise that's true. Okay, if you know B, you can get back to where you started. Or if you know the particular solution, you can get back to B, you just do the exact process the opposite way. It's just a headache. Yeah. Is it? Oh, you're definitely right. Yeah. 0, negative 1. My bad, my bad. Okay. That would get me to a totally different place and different solution set. So this would be where we would leave our answer. This is the solution set to the given set of equations. Okay, cool? Cool, yeah.
I know the homework solved.
Okay, let me take someone else. Yeah. 2.4. 3? Okay. Um, 2.4 problem 3, correct? True or false questions? Where'd he go? Yeah, is that right? Problem 3, 2.4. The true or false questions. Cool, got it. So true or false questions are what I think usually decide if a student is gets an A in this class or gets a B in this class. That's usually the deciding factor, is those sorts of things, all right? So, come on. There we go. So look, being able to understand what a true or false question is asking and being able to answer it correctly is usually the difference between getting an A and getting a B in this class. Okay. So here we have 5, 6 true or false questions, right? First one says the homogeneous system AX equals 0 has the trivial solution if and only if the solution, or sorry, the system is one free variable. Does a homogeneous system, so homogeneous means B is 0. What is the trivial solution? What is 0? X, right? Because it's trivial for us to say A times 0 equals 0. Of course, that is true, right? In fact, that's always true. It doesn't matter if we have a free variable or not. Okay. It is always true. A homogeneous system will always have the trivial solution. Okay, so this one's false. Okay. The second one says if x is a non-trivial solution to ax equals 0, then every entry of x is non-zero. Okay, what does non-trivial mean?
X.
Kind of, yes. It means that this isn't, x is not the zero vector. It doesn't mean everything in x is non-zero. Okay. For example, like x could be 1, 0, 0, 0, 0, 0. That is a non-trivial solution to a particular set of things. Okay. So this is false. It means one entry at least of x is non-zero. C, homogeneous linear system is always consistent. True or false? True. If my last column is all zeros, can it ever be inconsistent? No. Homogeneous, so that one was true. D says the solution set of a consistent inhomogeneous system, AX equals B, is obtained by translating the solution set of AX equals 0. True or false? True. What is it shifted? What is it translated by? The particular solution, VP. Okay, that is true. So, for example, if we go back to this question, another thing that a lot of students get wrong on something like this would be if AX equals B and B is non-zero has the solution set of this, what is the solution set of AX equals 0? And to do that, we just ignore this and we take what's left. It is as easy as that. You do not have to think any harder about it. Okay, does that make sense? Okay, is again, if you want to think about that, I said every B has a unique VP. Okay, the unique VP for solving equal to 0 is nothing. Okay, for solving a homogeneous equation, it's just plus 0. That's our unique particular solution for a homogeneous system. Yeah. Yeah, give me 1 second. B. If x is a non-trivial solution, then every entry of x is non-zero. It's just asking the definition of being non-trivial. And to be non-trivial means you have a non-zero entry, not all non-zero entries. So what this could be asking is it's saying like, so x is non-trivial. Does that mean that all of these numbers have to be 1 instead, or can they be 0 as well? They can be 0 because we still have this 1 up top. We just need one number to not be 0. We don't need all numbers to not be 0. Okay. So E says AX equals B is homogeneous if the 0 vector is a solution. True or false? True. That's true. Because if it is inhomogeneous, does my solution set touch the origin? No. So the origin is not a solution for inhomogeneous. Okay. Another way you can think about that, what is the only x I can pick such that a times x equals 0? Or sorry, let me rephrase that. If x is 0, what is a times 0 always? 0. So if x, the 0 vector is a solution, if I can use it for x to get b, I know I'll get 0 right off the bat. Okay. For f, if there is a vector b1, b2, such that the solutions to the following equation is the z-axis. Okay. So what is the vector that describes the z-axis, first of all? 0, 0, 1, right? Particularly the span of it. So like x, some x number times that would have to be our solution set, right? Looking for our solution set to have this. Okay. What you can do is you can sort of solve this for parametric vector form. You get x1 equals, it's going to be minus x3 plus b1. x2 equals b2. x3 equals x3. So we're going to get the x vector equals -1, 0, 1 plus b1, b2, 0. Okay. Oh, shit. It's x3. Okay. So is this line, is this vector parallel to the z-axis? No, right? This is what the z-axis looks like, straight up and down line. This vector, when we multiply it by x3, is -1 in x and +1 in z. Okay, so if I'm talking like x, y, and z coming out, it's basically coming like this. Okay, does that make sense? Yeah, they're coming like that. No. Unfortunately, for true or false questions, it's hit or miss.
So it's like A through F, and you get one of the problems.
Oh, no. Not like WebWorks or like, no. Each part is graded separately. Sorry, I totally misunderstood what you were saying. No, you can get one of these wrong and get an 80%, not a 0. All right. So this one was false. And the reason it was false was because this bottom vector I get down here, there is no way we can combine B1 and B2 just being a constant to get me the z-axis. Okay. All right, other questions? Yeah.
So.
1.1 problem 4. Okay, I'm gonna do something besides the true false after that, okay? Other questions? Yeah. 2.3, question 6. It's another true or false. Does anyone have any numerical questions? Yeah. Sorry, I'll get there, and if you have questions, come up and I'll explain it. Yeah. Wait, shh. What? 2.4, number 2. Alrighty. So this one is, given this giant matrix, give me the parametric vector form. So for something along these lines, it's exactly the process we talked about with that nice like curve at the beginning. We have it in, first step, put it in a matrix. What's my second step? Row reduce. Okay, so I'm going to get 1, -4, 2, 0, 4, -5. Augmented with -2. 0, 0, 0, -1, -4, 5, 3. And what I'm going to do is I'm going to go ahead and take row 3 equals row 1, or sorry, row 3 minus row 1. Okay, 0, 0, -2, 0, 2, 12, 4. Okay. So is your question about how to do the process, or? Sorry, say that again. About the general solution. So you're asking what is the general solution? Is that right? Yes, okay. So all the general solution is its parametric vector form. That's all it is, okay? If we get to parametric vector form, we get something that looks like this. And that just means get me there and show it to me, okay? Cool? Okay, other questions? Yeah. This one? Here? F? Okay.
I understand how you got the -0.
Yep. So what this is going to be is kind of hard to picture, but what do my B1 and B2 control?
The X and Y.
They control my particular solution only in X and Y, right? So they change how much I shift, right? So what this looks like is if we're graphing this in 3D without a particular solution, we're going to get -1 in X, +1 in Z. It's going to look like this. Graph is, the line is sticking out and going back into the graph, right? Where we're shifting by some X and Y to some degree, and then that creates a different solution set, okay? So B1 and B2 only control my shift, right?
Yeah.
They do not control what this line looks like, right? So this line, you can already see that it is not parallel to the z-axis, right? Will shifting that ever change that? No, that's all it's asking. Shifting it will never change how it looks. It'll just move it in space. Yeah, so it's asking for it instead to be this line that's sticking crooked. It's asking, can you get it to look like the line that sticks just straight out? And the answer is no, you cannot. You can get it to intersect it. You can never get it to be the same line. Is that? It's like if I say like, hey, my pencil faces this way, but I tell you I have something else that goes this way, and I tell you to move it however you want to get it to be the other one, you can never move it such that it's straight, right? That's what this question is asking.
Yeah.
Does that make sense?
Yeah.
Okay. Yeah.
Question, what if B1 was 1 and B2 was 0?
All right. What if B1 was 1 and B2 is 0? We have the x vector equals -1, 0, 1 times x3 plus 1, 0, 0. All right. Someone give me a value for x3. Start with 1. Okay. It's of particular interest here. X3 equals 1. What is my solution for that? X3 equals 1. That gives me the vector 0, 0, 1. Oh, that's the z-axis. No, it's not. It is a point on the z-axis. Okay, so if we instead took x3 to be 7, okay, this now gives us -6, 0, 7, right? We're changing x3, and yes, it will touch the z-axis, but that doesn't mean it is the z-axis. Does that make sense? Okay, other questions? Yeah.
How do you know when it's a point versus what is the z-axis?
So what you would have to realize here is the only important thing you're looking at is this vector. Okay. If B1 was here, for instance, if instead it was -1 minus B1, we could change B1 to be +1, and that would give me 0, 0, 1 with x3. Okay, but instead, it's over here, or where's this? It's in my particular solution instead of with my variables. So that's when it could change it, but that's not what we're set up to look at right now. Questions? Yeah.
Sound about that, it's a different question.
Any other questions about this? Yes. What?
You show how to convert the control problem into that parametric segment.
Yeah. So all we're doing is we're just moving from this. Rule number 1, put it in a matrix. 1, 0, 1, 0, 1, 0, augmented with B1, B2. Is this in reduced row echelon form? Yes, it is. So we spit back out equations. X1 equals -1 x2 plus B1, x2, that's x. X2 equals B2. And x3 equals x3. And from here, we move to parametric vector form and go from there. Cool. Other questions? Yeah.
It's a problem 2 on the midterm one.
Problem 2 on midterm 1B
Specifically.
from this semester.
Yes, specifically part.
Specifically part. Said midterm 1B, right? Problem 2B. Okay, this is a question that I've seen on just so many exams over my last few semesters grading. And if you understand it, you're in great shape for this exam on Wednesday. If you don't, I'll try to get you there. Oh. Lost it. Okay. Sorry, I was actually thinking of a follow-up to this problem, but this problem goes really well with a different one I've seen in a lot. But I have seen this on a lot of exams as well. So, are there three non-zero vectors that span a plane, but V3 is not in the span of the first two vectors? The answer is yes. Because have you guys talked about linear independence? Does that happen? Was that today? Okay, wonderful. This is a question that is easier explained by linear independence, but what it basically is talking about is why do we use our pivot columns for span? Okay, we use our pivot columns for span because by definition, when row reducing, a pivot column is a linearly independent column. It means it adds some new information, okay? And by adding some information, it's nothing you could have gotten from the columns before, okay? So what we need is we need a total of 2 pivots, okay? And if V3 is not in the span of V1 and V2, okay? Where does that mean one of the pivots has to lie? V3, right? So all we're doing is we're looking for 2 pivots, 1 pivot in the last column. So I would write this something along the lines of 3 non-zero vectors. It's fine. Does that make sense? It looks like this. You're just looking for any 2 pivots, okay? And anything above it can be non-zero. Okay. So if we're looking at another way we can talk about not being in the span is talking about consistency, right? So if instead it was this, is this system consistent or inconsistent? Inconsistent, which means V3 is outside the span of V1, V2.
Okay, so that's basically, I was just saying, like, have one vector be inconsistent.
Exactly. Yeah, when we were to augment it, you can think of it like that. Being inconsistent means it is literally independent of all of these before the augment part as well.
And then, so when I just said like span V1, V2, V3, is that talking about like column span or?
Yeah. We only talk about column span.
So it's only column span.
Yes.
It'd be like,
You see span 3 vectors, we're talking about like pivots, your pivots create your space, number of pivots and number of rows kind of spans.
and it says like V1, V2, V3, so that's how you know that there's 3 rows. And then like,
We don't actually. I just made that easy. Yeah. I just made life easy. These could be, if it said, sorry, it said vectors in R3. Being vectors in R3 means they have 3 entries.
Okay.
Yeah. But if it didn't say that, you could add as many entries as you'd like.
Okay.
Cool?
sounds good.
Yeah.
We expect to use set builder notation.
Say that again?
We expect to use set builder notation.
Set builder, no. If you know it, great, I'll understand it, but you're not expected to. Yeah,
So I have a question. I think
okay.
This thing is actually.
D?
Yeah.
Okay. Actually, before I do part D, but I am gonna note that I'm gonna do that next. One other question that I've seen a lot of is the same kind of vibe as part B, but it's 3 vectors in R3 such that span V1, V2, span V1, V3, and span V2, V3. Are all planes but span of V1, V2, V3 is also a plane. This one's rather difficult to kind of conceptualize right off the bat, but essentially it means I have 3 vectors, any pair of them has 2 pivots. Is it possible that when we have all 3 of them, there's still only 2 pivots? This actually is possible. The way we can think about this is there are three different vectors that lie on the same plane, okay? So the way I like to picture this is if I'm drawing in like 3D, okay, I'm instead just gonna look at the XY plane. I'm assuming Z is 0, okay? So I have a vector that looks like this and a vector that looks like this. How many pivots are there between them? 2, right? 2 different pivots, they're pointing in 2 totally different directions. Okay. Another way to do this would lie on the span of these 2 things, right? These 2 vectors, the first one, the second one, would create this whole plane, right? So this third vector lies on that plane. It doesn't add any new information. Okay. But any combination of these 2 vectors will still span a plane because they're still different vectors. Okay. That's to think about it geometrically. To think about it in terms of pivots, we'll start with span of V1 and V2. Someone give me 2 really, really easy non-zero vectors that span a plane.
1, 0, 0, 0, 1, 0.
That's perfect. Okay, how many pivots do we have? Okay, what do they span? Plane in R3. Okay. So now what we're looking for when we pair V1 and V3, and V2 and V3, we have additional pivots. But the span of them is still a plane. So if the span of them is still a plane, what does my bottom entry need to be? 0. Okay. Actually, for this, there's only one like really easy case, and it's if we have 1, 1, 0. It's kind of easy to show the answer and go backwards from here. So if we pair this with that last vector, how many pivots do we have? 2. Pair this with the last vector, how many do we have? 2 as well, right? And if we already said these 2 have 2 as well, right? So all we're saying is between any 2 of these, we have 2 pivots, but we never add a third. Just each one of them is in a slightly different direction on the same plane. So you can still construct a plane, but you can never build more than that. Does that kind of make sense? It's hard to explain this sort of thing in like geometrical and algebraic terms, but hopefully that kind of clicks. So. Other questions? Yeah. 2.44. 2.4, question 4. This is so much easier now that I have every page pulled up. This is the question on the particular solution. I'm so sorry, I said I would do D next. I'll go ahead and put these both in. Go. There you are. All right, so I'm going to do these 2. I'm going to call it a night. So we're going to look at part D first. Suppose A is 2 by 3. Right off the bat, what I'm going to do is I'm going to draw a 2 by 3 matrix. Okay. And suppose V is some vector such that the solutions AX equals V has the parametric form 1 plus X3, 2 minus X3. X3 is free. Select all that are true. So we have X1, X2, and X3. X3 equals negative X3 plus 2 equals X3 plus 1. Okay, this gives me the X vector is equal to 1, negative 1, 1 times X3 plus 1, 2, 0. Okay. So if this is a solution to my inhomogeneous equation, what is the solution to the homogeneous equation? Yeah, X3 times 1, negative 1, 1, which is exactly what question I is, or part I. Someone's true. Part 2 says for each B, the equation AXB is consistent. What does that mean? If all B are consistent, what is my span? Everything, right? I'm consistent everywhere. I span everything I can get anywhere, right? Does that make sense? So for each B it is consistent. How many pivots do I need for this to be true? Do I have 2? Yeah, that's true. Okay, and that's again going backwards. We have one free variable, so we have two not free variables, which create pivot columns. So that means we span all of our two, which means this is true. So this is the solution to AX equals V. Is V the zero vector? Yes or no? This was the solution. Why? We have a plus particular solution. Since this is here, this means V is not zero. If it is absent, it means V is zero. Okay, it's just that straight one-to-one connection like that. Yeah,
And that was literally just like saying like eliminate that particular.
that's exactly right. You just get rid of the constants at the end, and what you have left is the span of those three things. Any questions on that one? Yeah. So I like to tie consistency together with different things, right? Consistent means I have a solution, which means the B is in my span. Okay, do those three things being equivalent make sense? Okay, so for each B, it is consistent. So where do each B have to lie?
In the column.
Exactly. So all of my B have to be in the column space. All of them have to be in the span. They are in R2. How do I cover all of R2? How many pivots? 2 pivots. Do we have that? Oh, what's that? Questions on this one still? Yeah. If this was non-zero, it would be false. The third one. Oh, I got it backwards. That's true. That's true. That's true. I'm so sorry. I'm only human. Please correct me if you ever see anything wrong. Of course. Okay. Any other questions on this? Yeah.
What's the difference between the span and the span of the columns?
For the sake of this exam, nothing. Cool. All right. Any other questions on this one? Once, twice. Moving on. Okay. Last one. Suppose the parameterization for the solution set to the equation AX equals B is this, where X2 and X3 are free. Write a parameterization for the solution set to the equation AX equals 0. Using this information, use X to the blah, blah, blah. We're not typing this in. All right. This is my inhomogeneous solution. Okay. This is my solution to an inhomogeneous system. So, which of these things tells me it's inhomogeneous? The first thing, right? What do we call it? I like to call it V sub P, particular solution. Okay. If instead I'm solving for AX equals 0, what does this vector become? Yeah, it becomes 0. It goes away. So all we have to type in is this. We're done. Any questions on this? All righty. Wonderful. Good luck on y'all's exam. I'll be proctoring section A with a TA and Dr. Jankowski. Good luck. I've got my office hours tomorrow evening from 5 to 6. And email me if you have any questions or anything. I'm around. So yeah. Good luck and have a good night. Hey, can someone please turn the lights back on?